If we were to take a trip to Mount Everest to go measure the gravitational field strength, G, we would find that it's not quite 9.8. And if we measured it here, we would find just the same. It's not quite 9.8. 9.8 has been this approximate number that we've used as the gravitational field strength on the surface of the Earth, but based on how high you are on the Earth's surface or how close you are to the core, that 9.8 is going to be different at different locations. So today we're going to try and figure out the gravitational field strength here in New Haven using a pendulum. So here I have my pendulum, and it rocks back and forth in periodic simple harmonic motion. And I know that the time to complete one cycle is the period. In other videos, I derived for you this expression. The period is equal to 2 pi times the square root of L over G, where L is the length of the pendulum, so the measurement of the string to the end of this washer, over G. Now, this period is not for a pendulum released at this angle. This was derived using only small angles, so anything less than 15. So if I'm using this equation, then I should model this only with a small amplitude. It won't work. It falls apart if I lift this thing to a higher and higher angle. What I'm going to do is start here and rearrange this expression for L. So I take this, and I'm going to grab a few different colors here to do some board work. Here's my expression. I divide both sides by 2 pi, and I get this. Now to get rid of the square root, I'm going to square both sides. So I get t squared over 4 pi squared, because this square applies to everything in parentheses, is equal to L over G. Now I'm going to bring G over to the other side by multiplying by G. That cancels out. And I'm left with this equation. If I were to take data where I measure the length of my pendulum and then I measure the period for small angles, then I would get, and I took a bunch of data points, I would get a graph that looks something like this. Because t is squared, I get a parabolic function. Now, if I am going to try and find data and get a specific value about my data set, then I need to do some curve fitting. Think back to the beginning of the year where we had sample data and we had to try and fit that to a linear function. We're going to try and take this data and set it to be in the form of y equals mx plus b. So here's my equation, and I rewrote it right here. I want to get this in the form of y equals mx plus b, so I'm going to start to puzzle fit here. It should make sense that our y will be L. So on the y-axis will be L. The m here is going to be this constant. And here's my brown there. And x will be t squared. Notice that there isn't any other term like plus or minus another term in this equation. So b is 0, so I can just forget about that term here. Something just drops out. So I'm going to graph L versus t squared. And if I do this correctly, if I get proper data points, I should get a line. And if I find the slope of that line, then I get this value m. You can use any sort of linear regression app or your graphing calculator or Desmos. You put in the data into the data table, and then in a separate column you put in the expression form y1 with a squiggly, mx1 plus b, and then it will churn out for you values for m and b. And that m value is what you care about, because that is what's in red. And if you get that value, then you could solve for g. the way that you're going to set this up on your own whiteboards is with this data table. I want 5 different trials, so you should have 5 different data points like I have here. You'll measure the length with the washer on it, and then you'll take the time it takes to complete 10 cycles, and that would go here. So let me just give you some sample data. If I did 0.3 and it took 11.1 seconds the first time, I would fill it out like that. Then let's say I do it again, and after 10 cycles I get a time of 11.2, and I do it a third time. What do you know? I get a time of 11.3. What I'm after is the average period. So first I need to average all 3 of these together and then divide by 10 because there are 10 cycles. So my average is 11.2, but I divide that number by 10, so it's just like moving a decimal place over, and I get a value of 1.12, and that's in seconds. But remember, when we're curve fitting, we want to use L on the y-axis and t squared on the x-axis, so I'm going to square this value 1.12 in order to get something that is plottable for a linear function. So this would be the data here is my x, and the data for L is my y. So you'll do 5 different lengths. So with this setup, you could just roll up the plastic rod and change the height, then do it all over again. Plug that data into Desmos and you can get an M, which you can get a G from. When I did this, I got a % error of 0.03. So it is fairly accurate if you're careful in your measurements. On your whiteboard, I'm expecting to see 6 things. I want to see the algebra you did to rewrite the period of a pendulum for L, which I showed in the video. I want to see the data table with 5 lengths and 3 trial times for each length, the plotted time or the plotted data, and the line of best fit. Make sure that on the data table, or on the chart rather, you circle the data points so it's very clear where your data points lie. Then you're going to find the slope of the line using Desmos or another linear regression app. Finally, do some algebra to get the actual value for G, and then compare that to the actual G constant for New Haven, which is 9.798. So you'll use this equation, your G value minus what you should be getting divided by what you should be getting will give you the % error. So I will see you guys on Monday. I think I laid everything out in a straightforward manner. It should take you about 45 minutes to complete this. So enjoy the weekend. Good luck. I'll see you soon.